Okay, everyone. So, good morning. So today we're going to continue where we left off last week, looking at hydroformylation in a little bit more detail. And sort of where we left off last week was we were looking at the mechanism associated with the hydroformylation of alkenes using this guy here, this HCOCO4, which is the catalytically active species first discovered by Otto Röhrlen in the late 30s, just before the start of the Second World War. Important process because you can convert alkenes to aldehydes or ketones. This is the mechanism we looked at last week, starting from this catalytically active species, cobalt-1 formerly. You have a ligand displacement reaction over here, alkene coordination. You have sort of here an insertion reaction, a hydride insertion with concomitant CO coordination. Concomitant means at the same time. So sort of two steps in one represented here. Then you have a migratory insertion to form this acyl group here. And then this reacts with hydrogen to form the product and regenerate the catalytically active species. And we discussed last week that this reaction with hydrogen could occur via sigma bond metacatecal route or via formal oxidative addition. In principle, and there's some speculation as to how that proceeds. In any event, this is sort of the simplified mechanism of hydroformylation. Now, in terms of this cobalt catalyst, it's been found that the rate determining step is in fact this last step here involving the reaction of hydrogen gas with this acyl complex here. And that's not always the case. I mean, depending on the catalyst system and depending on if you sort of modify the ligand sphere around the cobalt, so that's not always the case that is necessarily always the rate determining step. This is what we looked at last week. You know, does it occur via sigma bond metathesis or oxidative addition? Both are in principle possible. Yeah. Now, this is sort of an extension of this catalyst cycle by Mehrbach. So, what he basically, this sort of incorporates the pre-catalyst. So, COHCO4 doesn't exist in a bottle. It has to be generated somehow. So this is the active species. It is derived generally from this dinuclear cobalt compound, dicobalt octacarbonyl. This is something that you have in a bottle, right? So what actually happens is you throw this into the reactor, and then this is the pre-catalyst. It's generated by reaction with hydrogen. This is a slow process. But this is the sort of the catalyst activation step to generate 5, which is the active species. Now, an interesting sort of thing to point out here is that the last step of this catalyst process, which we just looked at, can in fact also be facilitated, look at what's happening here, by reaction of some active catalyst species with the acyl. That's a possibility. Right? An alternative possibility. So if 5 reacts with 7, check what's happening out. Basically, the hydride of this cobalt is passed to this cobalt atom here, right? And then you have a reductive elimination and you form the product directly. And of course, if you've plucked off a hydride here, you're back here. Of course, you'd end up with COCO4, which would then undergo dimerization to regenerate the CO2CO8. That's an alternative pathway where you can get from here to the product, right? And of course the other alternative is what we've just looked at, where this reacts with hydrogen to form the species here. So this is a proposal by a guy named Mehrbach. That's an alternative possibility that in fact the last step of the reaction is hydride transfer from 5 to 7, reductive elimination and regeneration of the active catalyst species, which then reacts with H2 again to form the active catalyst, or alternatively, you have this process happening first and then you have this cycle. So those are the two possibilities. Now that's sort of the basic original work done in the late 30s with cobalt carbonyl hydroformylation. And of course, it's a very robust system, and it's very good in converting alkenes to aldehydes. Now I should mention, remember you have this business of N and iso. You can either get, if you have a terminal alkene, remember we discussed this sort of briefly last week. If you do hydroformylation, you can either get something like that, or you can get something like that. So this is the end product, this is the iso product, okay? And basically, it turns out that industrially, what's much more desirable is the end product, because you can do stuff with that, right? If you've got an aldehyde functionality, you can convert it to carboxylic acids. You can do it's a useful handle for further functionalization, whereas the iso is less desirable. It's not completely useless, but it's a less desirable product from industry. Now, let us go on, and let us now ask the question: what if we now do the reaction with carbonyl, with phosphenes instead of carbonyls? What's going to happen there? And this is work that was done in the late 1960s by a guy named Slaw. And what basically he did was he said, okay, let's throw some phosphenes into the reaction mixture and see what happens to the active, to the rate of the catalyst. Does it increase or decrease? And let's look at if we can change the N to iso ratio by changing the ligand. So instead of using HCO4, which is the original, let's say, first generation system, Otto von Ruhlen, or Otto Ruhlen, let's throw in phosphenes, which will then basically react with the HCO4, COCO4, and generate a species like that. Now, the interesting thing is, if you imagine doing that, okay, as we see in this graphic here, one of the key steps, as we know from the catalyst cycle, remember, is the insertion into the cobalt hydride to form an alkyl, right? That's one of the key steps in the mechanism, which we see here, right? There we have the hydride insertion. Now, if you put a bulky, these are pretty sterically demanding phosphenes onto the cobalt center, there are two possibilities. It's either going to insert into in this way, in a anti-Markovnikov way, or in a Markovnikov way, right? In other words, you can either put the H in during this insertion process on that carbon atom there, or on that carbon atom there. If you put that H, if insertion happens in such a way that that H is migrated there, you're going to end up with this product here. And if the H goes to the C1 atom here of the alkene, you're going to end up with the anti-Markovnikov addition. Those are two possibilities, yes.
So would it be called 1,2 insertion and 2,1 insertion? Like, is that a difference?
Yes, 1,2 and 2,1. Now here's the thing, guys. Which of those two do you think is more favorable? Sorry?
The Markovnikov.
All right, let's just write down the structure of this phosphate.
Does it depend on the R group?
It does.
Because then anti-Markovnikov would be more favorable if the R group
It's
is
boron or something.
Yes, yes. Let's write down Bu as butyl. So this phosphine is this guy here. That's butyl. That's pretty big, right? You've got these arms hanging out. So that phosphine over there, that situation over there, the sort of tetrahedral intermediate, right, is going to be slightly, in fact, slightly more preferred than this guy here, because look at the situation. imagine these two groups are pointing on both sides of the cobalt. On the top structure, it's only on the left-hand side you effectively have like a steric interaction between this alkyl chain here and the pretty sterically demanding phosphine. Do you see that? In the bottom structure, right, and this CH3 is pointing away, right, so it's not really of any consequence. But here, in the bottom structure, you've got CH3s on both sides of this axis here, and so both of these are going to interact with a tributyl phosphines. There's going to be some steric interaction there. So the structure that has the minimum steric, let's say, pressure or interaction is in fact the top structure. And if the top, if we now in this intermediate, remember it's a catalyst cycle, prefer or steer it that we selectively get the top structure, are we going to end up with N or iso as the main product?
N.
Sorry?
N.
N. Why N?
It would be at the end of the chain because your hydrogen is.
Well, what's going to happen now is this is going to react with another equivalence of CO. We're going to get migratory insertion, and then we're going to get and then we're going to get reductive elimination, isn't it? According to our original cycle. So if you end up with the N chain, you're going to have an improved selectivity towards N, a skewed selectivity towards N. And another way of looking at it is, if we look here at the bottom, this is now looking at the sort of the intermediate that you form, or let's say the transition state, showing an insertion. The two possible insertions of, okay, in this case we just have one p-butyl group. There we've got two. Doesn't really matter. The reasoning is the same. If we look at this transition state on the left here, you know, this is basically just preceding the hydride insertion of the alkene. You can see that the R group here is pointing sort of out of the plane of the board, right? And the butyl is pointing back. So that's a minimum, that's not so bad, right? Because these two big groups, R is representing an alkyl chain, for example, are pointing away from each other. Whereas this structure here, check it out. What's happening there? Both of these sterically demanding groups are pointing in the same direction. That means that this is going to be undesirable. This will lead to the Markovnikov addition. This is the anti-Markovnikov addition, which would then, of course, give a high selectivity towards N following the migratory insertion and reductive elimination. So that's sort of what's going on here. When people realized this, they went into the lab and tested it. And a seminal paper in this regard is by Slaw, 1968, Journal of Organometallic Chemistry. There's the reference, where they did the hydroformylation with lots of different phosphines to see what happens using these arguments that I've employed here. And these are the results. This is taken directly from their paper. Something I haven't mentioned is that one does also tend to get alcohols as products in these hydroformylation reactions, because of course you've got lots of hydrogen floating around, right? So it's possible that you could get first the formation of an acyl reductive elimination to an alcohol. But let's not worry too much about that. Let's concentrate on the aldehydes. Now, these are the different phosphines that they've employed, okay? Now, if we look at this data, this is the original data from this Slaw paper, Slaw and Molinol, I think was the other guy's name. I don't know if I've pronounced that correctly, but anyway. There's two issues. There's always two issues in catalysis. What are they? First issue? Activity and selectivity. Those are the two drivers in evaluating whether a catalyst is good or not. Now that's what we have here. We've got rate of gas, right? This is the sort of a way that they've measured the rate of the reaction. But look at the selectivity. Here we're looking at the N to iso. So iso is branch. branched, right? You can also call it the branched product. Now, what do you guys notice? Well, which is performing the best here? Remember, we want the N. The N is the industrially desired one. Which one is the winner? Butyl. Okay. Now, butyl is pretty big. Okay, there's the butyl. But here we've got, for example, triphenyl phosphine, which goes down to 66. That's pretty low. And we've got some other intermediates here, like, or some other phosphines here. Like here we've got diphenyl ethyl, which is at 74. So, and here we've got tricyclohexyl phosphine, which you know, goes up to about 80. So it's kind of difficult. Do you agree with me to delineate what's going on here? It seems to be jumping all over the place. I mean, one thing's for sure. One basic comment is if you compare all of these to, let's say, just doing it with cobalt COCO8, you do improve the selectivity towards N by adding a phosphine, right? And that's because of this Markovnikov, anti-Markovnikov story. With the cobalt, it's going to be pretty random, right? It's not, there's no, if you just have, with the carbonyl, if you just have carbonyl groups here, you're not going to sort of skew the distribution one way or the other. But by adding a phosphine, you do, because of these arguments here. So the fact that the sort of the basic take-home message is that you improve the N to ISO selectivity by adding a phosphine. But the question is, how do we rationalize the differences within this data set? That's not so easy, okay? As you can see here, I mean, it's kind of hit and miss. It's all over the place. I mean, if we use a chelating phosphine, like here we've got a couple of those, right? The selectivity sort of drops, but it's again difficult to delineate this because if you've got DPPE, that's the abbreviation for this chelating phosphine, it's 56%, and then if you just remove one carbon in the backbone or you add one, then it changes. So it's difficult to draw any conclusions from this. So fortunately, a guy in the mid 1970s named Tolman, who was a scientist at another one that worked at DuPont, which is incidentally the same place that Schrock worked at, you might recall. And actually, he was a very interesting character. He never really worked as a professor at a university, per se. He worked at DuPont for a very, very long time. And in his later career, sort of when he got older, he's still alive, he devoted his life to fighting for climate change, you know, and trying to alert people to the importance of climate change. He did teach some courses briefly at the University of Delaware, and the University of, and some community colleges there and stuff like that, but he really stayed in and around Delaware, right, which is a state, a very small state on the east coast of the United States, sort of close to New Jersey. I think it's sort of borders on Maryland. So I think he's quite an interesting character because he did all of this work in the 1970s, and if you look at his publication record, there's this explosion of papers in the 1970s, and after that, not so much. Interesting. But he did this work in the 70s, and what he tried to do now is exactly what we're discussing now. Let's delineate these this data, right? Inspired partially by the results that he saw in catalysis involving phosphines. And he came up with two parameters. The first is called the Tolman angle, named after him, and basically this is a measure of the steric demand associated with a phosphine, and the way that it's determined is you take a metal, you take this red atom represents the phosphorus, you put it at a distance of 2.28 angstroms from the metal. That distance was selected because they looked at all crystal structures of phosphines and found that that was sort of the average distance between a metal and a phosphorus atom. And then you take the substituents, phenyl, butyl, isopropyl, whatever, that's on the phosphorus, and you draw a cone around it. You draw a cone around it, and the angle of that cone is called the Tolman angle. Very simple, okay? So you've got the so of course the more sterically demanding the substituents, right, the bigger those balls are going to be, and the bigger the Tolman cone angle. The bigger the angle, the more steric demand it has. Does everyone follow that? So that's the so-called Tolman angle.
Didn't do the same study with the Catholicism, the groups, the bike angle?
No, that wasn't really involving phosphines, but that was also, I mean, you can change the steric demand, but that's not really got anything to do with phosphines, right? Here we're talking about phosphines as ligands in hydroformylation.
So this study was only the phosphates?
Yes, yes. This is specific. This Tolman cone angle is specific to phosphine ligands. So that tells us about the sterics. But you know, in chemistry, there's always two issues. The one is sterics. What's the other? Electronics. Right. I've always liked that term electronics because it makes it sound like you're working on circuits or something. But okay, that was a silly joke. But exactly. So this parameter tells us about the sterics, but there's more to it. Electronics. So he came up with this. Well, that's just again a representation of the cone angle. This is for trimethylphosphine. This is how you would sort of define it. And that's the Tolman cone angle, just as an example. That's sterics. Now we need to find a way of understanding if a phosphine is a good electron donor or a poor electron donor. And how do we do that? We make a series of complexes. This is what he did. You take nickel tetracarbonyl, it's nickel 0. You react it with a phosphine of your choice, okay? You do a substitution, you end up with a C3V symmetric system like this, with L representing the phosphine, and you record an infrared spectrum. Now, I guess I mentioned this into the 2000s. Maybe you've had this in some other courses. Transition metal carbonyls are great in infrared spectroscopy because they absorb beautifully and you get these beautiful absorption peaks, right? They're strong, they're very infrared active. Now, basically, what does infrared spectroscopy tell us, right? If we get an absorption at a certain wave number, what does it tell us? It tells us about the strength of that bond, right? If we've got a high wave number, it's strong. And if the wave number is lower, it's a weaker bond. Now, when we attach a phosphine to nickel, right, what's going to happen? Well, we're going to have a setup like this. Remember the Dewar-Chat-Duncanson model? That's basically what's going on here. If the phosphine is a strong sigma donor, a very strong sigma donor, and a poor pi acceptor, because phosphines are sigma donors and, believe it or not, pi acceptors. They're not very strong pi acceptors, but they do, like carbonyl, have pi accepting capacity into the pi star antibond of the phosphine. But anyway, if you modulate the R groups here, right, it's going to change the sigma donor and pi acceptor capacity. If the thing is a very strong sigma donor, what does that mean? It means you're going to push a lot of electron density into the metal, make it electron rich, and what's the effects of that going to be? It's going to facilitate more pi back bonding to the carbonyls, right? So if you push electron density in, lots of electron density from the phosphine, in other words, if it's electron rich, this guy becomes very electron rich, and that means more pi back bonding to the pi star orbital of the carbonyls, which means what for the bond strength? No. If I populate the pi star orbital, weaker. So stronger. So the conclusion is more electron-rich phosphines, weaker CO stretching, weaker CO bond because you're populating the pi star orbital. Review the Dewar-Chat-Duncanson model, right, to refresh your memory. And if you're populating the pi star orbital because this guy's pushing electron density in there, you're going to see a stretching vibration for the CO at a lower wave number. Now let's play it the other way around. Let's suppose the phosphine is not that electron rich. Or let's say it's picking up electron density for whatever reason via a back donation from the metal. That's going to result in a decrease of electron density on the metal, on the nickel in this case, which means there's going to be less electron density available for a pi back donation to the carbonyls, which means you're going to have a stronger CO bond, which means it's going to have a higher stretching vibration in the infrared spectrum. So let's write that down. Right? Strong, so electron rich, or let's say electron pushing phosphine will increase the electron density at nickel, right? Which results in increased pi back bonding to pi star orbital of CO, which results in a weakening of the CO bond strength, which results in a lower wave number, right, in the infrared spectrum. So do you see how nice this is? You can actually, just by recording an infrared spectrum, say something about the electronic characteristics of a phosphine. Great. And that's what Tolman did. And by the way, you can turn this all around and do it the other way for electron poorer system. So now we've got two nice parameters. We've got one reflecting the steric demand and one reflecting electronics. We call this the Tolman electronic parameter. We call this the Tolman electronic parameter. And so now we've got the cone angle and we've got the electronic parameter. Yes?
If the substituents on the P is different, then how do you calculate the cone angle?
Well, you've got to model it. Right, you kind of got to build a model, right, and you can do that, right? You can either build a model or generate a computer, it's not that difficult.
Mm-hmm.
You can simulate it. So there's some simulation involved, I mean, or you can look at a crystal structure. But the easiest way is just to build a model on a computer and build a cone around these substituents, and then you can see what the cone angle is. Mm-hmm. Which is what you see over here. It's actually not that difficult. And as you can see, this is experimental results. Now, so what Coleman then did, he said was, okay, there's always two factors in chemistry. There is sterics and there is electronics. We have to consider both. So what he did is he mapped it. He mapped the sterics and the electronics, and he came up with something like this. So what we have here is the stretching vibration in reciprocal centimeters in wave numbers of these different phosphines, doing basically what I just described here. On the y-axis and on the x-axis, the Tolman cone angle, right? So this gives us a pretty good idea of sterics and electronics, and it's a very cool and nifty tool to have, because check this out. What does this tell us? It tells us, for example, that these guys here, right, are well, the wave numbers are quite small, so are they very strong electron pushing phosphines or not?
Yeah.
Yes, because the wave number is lower, more pi back bonding, lower CO bond strength, exactly. These guys at the top here, PF3, is that a strong electron pushing phosphine? No. No, it's not, right? And of course it's not. Why? Because of the fluorine, which is electronegative, which sort of resists the lone pair sitting on the phosphorus to form a strong sigma donation. So that table is quite nice, and you can see on the x-axis we have the steric parameters. Now let's try together to delineate the original results of SLAW using this table to see if we have any results. Let's do that. So what I'm going to do is I'm going to erase this, and let's see if we can figure something out together. You'll see it's not so trivial. All right, let's have a look. All right, so what SLAW did, these are the results, is he did hydroformylation of 1 penti. Okay. 1968. The Summer of Love. Okay, now, so we have here the best one. Let's now consider selectivity towards N. Let's look at only, not activity, just selectivity towards N, which is normal. Which is the best one? We said it is the butyl. 91. Here's the butyl. Alright, what comes next? This guy here. Now, I don't think that this is actually on this map. Unfortunately, they don't have it. So let's go to the next best one, which is yes, but okay, these are different temperatures. So let's consider, okay, let's only consider 195, 150 degrees. Alright, let's keep the temperature the same. Alright, because there's two different temperatures. So let's try and do this together. Alright, this is a fun exercise. So that guy's still pretty good. At 150, it's 91. Okay. This one is 81, the triethyl, which is right next to it, so that's pretty good.
It's a different temperature. No, let's choose 195, there's no 150.
There is.
Alright, shall we choose 195? Okay, fine. See, there's a lot of parameters that affect it. Alright, so the butyl is still pretty good at 195. The ethyl is 81. So let's include that. The black ones are the good ones. P-cyclohexyl is 79. Alright, where is that? That's over here. That's not too bad. Let's take everything above 75. Alright? What else?
80.0.
Number 6. P2pH. Here it is. Look at that. See, we're starting to see a pattern. What else? P8pH is not so good. There's pH butyl 2, but it's unfortunately not on this map. I don't think. Unfortunately not there. Alright, but I mean that's sort of a, are there any other ones above 75? Let's disregard these here because this is with arsenic, and let's disregard the binentech ones. Okay. Alright, so that's basically, we see at least, we're starting to see some sort of a pattern. What do we see? We see that phosphines typically that have, according to this data that we have here, that have that are strong sigma donors and not excessively large, tend to be good in steering the N-to-iso ratio. Point is, it depends not only on the size, but also on the electronics, okay? You cannot delineate it just by looking at one, you've got to look at both. Now let's look at some ones that are really poor, okay? Let's do those in blue. What about at 195? Let's see. Alright, the triphenyl, this one here, is the triphenyl phosphine. At 195, it's got a selectivity of 66. That's pretty poor. We've said we're going to disregard these. So what do we have left? We've got number 5. Yes, again, that's not really, unfortunately, on this map.
And 67.2. That's not.
No. You see, it's so it's quite limited. What else do we have? Is that all?
74.5 maybe.
74.5, yes, but I've said we're going to disregard these because this is not comparing apples with apples. These are binary. Number 7. Oh, there.
That wasn't only
But I don't think we've got that one on the table. pH2, or do we? We've got P2pH, but we don't have. Anyway, So we've only got one data point. That's not really that's not really useful. But the fact of the matter is that I think this is quite convincing here, right? So this seems to be a quadrant for steering a good isoselectivity. The fact that the take-home message is it doesn't just depend on the size. It also doesn't just depend on the electronics. It depends on both, right? Because you can see they sort of jump all over the place. So that's the great contribution that Tolman made. Now, fortunately, I've got more data here. This is for one hexene hydroformylation with different phosphenes. We're going to play the same game with this now. This is done by someone else. And we're going to look at the effect on rate in a moment. Now, basically, just one or two comments. You see what the hydroformylation conditions are. You basically take the precursor CO2-COH, right? That's, remember, the sort of the, let's say, zero or first generation system, 1938 Ruhrchemie. You throw in phosphenes, you pressurize it with syngas, bless you, and you do the reaction, and you basically analyze the products by GCMS, and you can also see we have you can measure the rate. So we're going to look at this as well now. But before we look at the rate, again, look at the N2-isoselectivity. And I hope that I have, all right. So what I'm going to do now is I'm going to copy this table again into this, and let's see if we can delineate it. So this is what you would do if you were a scientist. You would have this data and you would say, okay, let's try and make sense of it, which is not always so easy, right? That's the point. Okay. Is that big enough? Yes. All right, let's play the same game. Black is good, blue is bad. All right? You see the tributyl phosphine, so this is now one hexene, not one pentene, one hexene. Basically the same trend holds, you'll see that in a moment. 90% N, 90% N, tributyl. 89% tripropyl, which is not on this map. Isopropyl ethyl. Here's ethyl, PN3. PN2PH is over here, all right? You see they're all pretty good. That's 85, that's okay, we'll put it in. P-isopropyl, I don't see it, here it is, okay. So p-isopropyl and P2PH we've put in. PH2 is unfortunately not on the map. But anyway, those are the good ones, the very good ones. Do you agree? All right? I know it's not very clear, but you can more or less see it. Now, which ones are really poor? Again, you see we have the same trend. Let's do it in blue. Triphenylphosphine, which is over here. And, yeah, again, we unfortunately don't have this data set here. P8PH2, is it not here? Okay, again, we have a very similar picture to what we saw for the 1-pentenes hydroformylation. In fact, the picture is identical. Isn't that quite interesting? The take-home message is we've actually got one extra data point here, this one, right? And we can see, so basically what we can now sort of say with a bit of hand-waving arguments is that it seems to depend more on what? Electronics. Yes, because here we've got a pretty big cone angle, and here it's quite small. So electronics seem to be more important than sterics. So you see why this is important. In fact, in the previous study, we had a data point for PCY3 as well, and that was also good, right? So let's just check that out. Let's go back to the 1-pentene data. PCY3, cyclohexyl, was also acceptable according to the criteria we employed there. So this one you can actually, if we combine both data sets, this is also a black data point. So you see, these are all good, but we have quite a big variation in the sterics. But the connecting thing is that they both, that they all seem to be pretty strong sigma donor ligands, which means that that seems to be driving the selectivity.
Everything
Yes.
above that line has a electronegative atom.
Which means?
Yes.
Which means it's a poor sigma donor, exactly. Everything above this line, the wave numbers are getting bigger, which means it's a weaker sigma donor, which means that there's less pi back bonding, which means the CO bond is stronger, which means that you see the stretching vibration at a higher reciprocal wave number. So this is quite interesting, I think. Now let's look at the trend. So that's selectivity into ISO. Point is, take home message, you can steer it by using different phosphenes. Very interesting. What's the other take home message? Let's look at the rates. Do you see there's actually quite a straightforward trend there? K is the rate constant for the reaction. What do you see? Disregard the first data set, the isopropyl. You see a very clear trend between what and what. The rate increases as cone angle increases. Now why would that be? That's an interesting thing.
Because you're kind of
It doesn't really though, because there's a top one that has a bigger cone angle and the other ones it's going.
Well, let's have a look. Let's look at this. The cone angle. No, the cone angle is increasing. Look at that from 132 to 145. And if we disregard the top data set, on average we go from 2.7. The K value is increasing. So there is a, if you like, some sort of a correlation. On average, there's always going to be exceptions between cone angle and rate. The bigger the cone angle, the faster the rate on average. Why?
because you're kind of steering the monomers to the metal side. I mean the reactants to the metal side.
Let's look at the catalyst cycle. Let's look at the catalyst cycle. No, that's not the right answer. But let's look at the simplified mechanism. Now, if I install over here, if I replace one of these COs, or even two of them, with a big R group, okay, with a big phosphine, sorry, containing very, very big R group, so it has a big cone angle. What's that going to do? What it's going to do is in this step here, right, which is the migratory insertion, when this CO goes and sits on that metal, it's going to, because the phosphines are good, it's going to be so sterically congested around the cobalt with these big phosphines that it's going to force the migratory insertion to occur at a much faster rate. So the phosphines come into play. The bigger the phosphine, the faster the migratory insertion. In this step here. Because these guys are big, is now, let's say if we do it in a stepwise fashion, the CO goes on, and you've got this very congested cobalt center, which is then going to say, okay, I'm too congested, and it's going to do the migratory insertion at a faster rate. So that's why we see this trend. So you can steer the selectivity, and you can steer the activity. Julia, you look confused.
Yeah, could you explain it?
All right. This is the mechanism. If the CO goes and sits, if we have this intermediate, the alkyl intermediate, and the CO goes and sits onto this alkyl intermediate, right, as another intermediate. The step that comes after that is the migratory insertion. Now, if we have a CO sitting here, right, in this intermediate, remember these are very sterically demanding groups, the cobalt center is going to be sterically congested, isn't it?
Mm-hmm.
And because it's sterically congested, it's going to facilitate that migratory insertion faster, because the migratory insertion is where the CO, inserts into the metal alkyl bond, so you get it away from the cobalt. So it's about relieving the steric congestion around the cobalt center. So the bigger the phosphine, the faster the migratory insertion, the faster the rate of the reaction. Yes?
And in that case, like, if we have like a lot of steric hindrance already there, why does it even go there? Why doesn't it just say, I don't want to do this reaction?
Okay, well that's a good question. It's because you must remember that this reaction is taking place under high pressures, right? So typically 50 bar pressures, there's a lot of CO around. And a carbonyl is quite a small molecule. And the cobalt center in this intermediate, this alkyl intermediate, is electronically not that happy, right? So it's going to see the carbonyl, it's going to grab hold of it, and it's going to facilitate the migratory insertion. So the cobalt is kind of hungry for electrons. But then it bites off more than it can chew. So it grabs the carbonyl, the cobalt center is electronically congested, and then it says, oops, I've bitten off more than I can chew. Let's do a migratory insertion as quickly as possible to alleviate the steric pressure around the cobalt, and then you increase the rates of the reaction. Everyone follow? Okay. Now, let us soldier on to, so that's Tolman angle. Now, we've looked at basically adding, we've now looked at adding phosphines to the cobalt system. Now, surprise, surprise, you can do hydroformylation with rhodium as well. And they did this also in the mid-1960s. In fact, I've done some work with rhodium hydroformylation myself. It works like a bomb. Cobalt works great. Rhodium works at least sometimes 100 to 1,000 times faster. Okay? Rhodium is much more active in hydroformylation. Now, this complex over here is something you can actually buy. It's a yellow substance, it's a crystalline compound. This is a great pre-catalyst for rhodium hydroformylation. And of course, what you can do, so with cobalt it was CO2CO8, that was the pre-catalyst. Here with rhodium, this is an example. I mean, you have many other rhodium sources, but this is sort of a classic example of a rhodium hydroformylation catalyst. And the mechanism is exactly the